So today we're going to be looking at random variables. What are they and how to operate with them? As always, we'll begin with a story.
The ruler of Livornia sent 5 emissaries to neighboring lands to seek out help against the pirates of the Birinian Sea. The ruler believed that each emissary had an 80% chance, independent of the others, of making it to their destination successfully. What is the distribution of the number of emissaries that successfully reach their destination? Our focus up until now has been on events. Now consider mathematical objects that are called random variables. A random variable is similar to a variable, except that partial information about it is available. For instance, if X is the roll of a fair six-sided die, it is possible to say that X is in 1, 2, 3, 4, 5, 6 with probability 1. Moreover, statements like X equals 1 can be assigned probabilities. If it is a fair die, then the probability that X equals 1 is 1/6 by the principle of indifference. Statements like X equals 1 can also be written using set notation. X equals 1 is the same as saying that X is an element of the set containing only 1. Set notation is very general. For instance, the event that X equals 1 or 2 can be written as X is an element of the set 1 and 2. Note that the set containing 1 and the set containing 1 and 2 are subsets of the state space 1, 2, 3, 4, 5, 6. In general, a random variable X has a number of sets A such that the probability that X is in A is defined. The collection of all such sets can be written as script f sub x. We say that X is a random variable if there exists a collection of sets script f sub x such that the probability that X is in A is defined for all A in the collection script f sub x. For example, in the story that started this chapter, let n be the number of successful emissaries, and n is a random variable. Because n is in 0, 1, 2, up to 5 with probability 1, the collection of sets that can be assigned probabilities is any subset of 0, 1, up to 5. If the probability that X is in A is defined, we say that the set A is measurable with respect to X. For the random variable n, the set of measurable sets with respect to capital N, script f sub n, includes the empty set, the set that only contains 0, the set that only contains 1, and in fact, every single subset of the set 0, 1, 2, 3, 4, 5. Because there are 6 possible outcomes, there are 2 to the 6th power, or 64 measurable subsets for n. Now, the function that takes as input a measurable set, A, and returns as output the probability that X is in A, is called the distribution of the random variable. In general, distributions of random variables are functions, capital P sub X, that take as input script f sub x, a set from that collection, and outputs a number 0, 1, which is the probability that X is in A. We write X tilde P sub X to mean that X has distribution P sub X. Now, some distributions occur often enough that it makes sense to give them their own names. Consider random variables that come from rolling dice. We will write X tilde dn to mean that X is a random variable where the probability that X equals I is 1 over n for all I in the set 1, 2, 3, up to n. We say that X is the roll of a fair n-sided die. Now, the symbol tilde is used to denote the distribution of a random variable. The random variable name goes on the left, and the name of the distribution goes on the right. Now, suppose that we have X distributed as this n-sided die roll, and we want to find the probability that X falls in a set A. Well, one thing that we can do is we can sum as I goes from 1 to n of the indicator that I is in A. That's going to count the number of elements of A. And then we divide by n, because each one of those elements has a 1 over n chance of occurring. This works because the only possible values for x are 1 up through n. The probability that x falls in this set equals 1. If we have a sequence, a sub 1, a sub 2, and so on, such that the probability that x falls into that sequence equals 1, then we refer to x as a discrete random variable. For a discrete random variable, if you want to know the probability that x falls in a set A, you sum over all possible values that it could take on the indicator that a sub I falls into the set A multiplied by the probability that x actually takes on that value. So for a discrete random variable x, to determine the distribution of x, it turns out, because of this formula, it's enough to say what the probability that x equals I is for any such I that this value is a positive value. Now, in the stories, each of the 5 emissaries was sent to a neighboring land. Each journey was a success independent of the others with probability 80%. So if we use the letter S to denote a successful journey and F to denote a failed journey, we might have an outcome like SSSFS. That would indicate that journeys 1, 2, 3, and 5 were successful, while journey 4 was a failure. Because 4 journeys were a success, the number of successful journeys, n, equals 4. Now, using independence, the probability of getting exactly that set of outcomes is going to be 0.8 times 0.8 times 0.8 times 0.2 for the failure times 0.8, or 0.8 to the 4th power because there were 4 successes, and 0.2 to the 1st power because there was 1 failure. But of course, SSSFS isn't the only way to have 4 S's and 1 F. We could have FSSSS or SFSSS. In fact, that 1F can go in any of 5 positions. And so there are 5 different ways of having 4 S's and 1 F in a 5-letter sequence. Multiplying that by the probability of each sequence tells us the overall probability that n equals 4, which is almost 41%. Now, a bit of combinatorics is going to tell us exactly how to find the number of 5-letter sequences with exactly I outcomes that were S and 5 minus I outcomes that were F. And what those are called are binomial coefficients. So definition: the number of n-letter sequences where you have exactly I letters S and n minus I letters F are called binomial coefficients and are written with the n over the I enclosed in parentheses. This is read aloud as n choose I, because we're choosing out of the n letters which of the I letters are S. In order to calculate the binomial coefficients, choosing I letters to be S is the same as choosing n minus I letters to be F, and both binomial coefficients are n factorial divided by I factorial, and with another n minus I factorial in the denominator. Now, the factorial function, n factorial, starts at n, multiplies by n minus 1, and goes all the way down to 1. For practical purposes, we take 0 factorial to equal 1 as well. So for instance, if I wanted the number of 5-letter sequences with 3 letters S and 2 letters F, that would be 5 choose 3. I'd have a 5 factorial in the numerator and a 3 factorial and 2 factorial in the denominator. That is 5 times 4 times 3 times 2 times 1 in the numerator, 3 times 2 times 1 in the denominator, and a 2 times 1 in the denominator. Canceling out as much as possible makes it easy to calculate that as 10. So similarly, we can find 5 choose 4, 5 choose 5, 5 choose 2, 5 choose 1, 5 choose 0. And when we do that, that's going to give us the following table of probabilities. Now, the probability that I equals 4, we already calculated to be 0.4096, but we can calculate all the other probabilities as well. From the fact that I talked about earlier, that's enough to tell us the distribution of the random variable n. Now, earlier we talked about events being independent, which means that the probability that both events occur is the product of the probability that each individual event occurs. For two random variables to be independent, for all pairs of measurable sets, the event that the two random variables are in these sets must be independent of each other. So in other words, if I'm interested in random variables x and y being independent, it must hold that for all sets A measurable with respect to x and B measurable with respect to y, the probability that x is in A and y is in B should factor into the probability that x is in A times the probability that y is in B. Now that's a lot of conditions to check. For instance, if x is the roll of a 6-sided die and y is the roll of a 4-sided die, there's 2 to the 6 measurable subsets with respect to x and 2 to the 4th subsets that are measurable with respect to y. Multiplying 2 to the 6 times 2 to the 4th gives 2 to the 10th, which is 1024 pairs of subsets to check independence. There's got to be a better way. There is a better way. Here's what we do. Suppose that x has to take on x1, x2, x3, so on. And y has to fall in the sequence y sub 1, y sub 2, and so on, both with probability 1. And it turns out x and y are going to be independent if and only if the probability that x equals a particular x sub I value and y equals a particular y sub j value equals the product of the probabilities that x equals that value and y equals its value for all I and j. Now, one direction is pretty easy. If you set the measurable set to be the set that only contains xi and the set that only contains yj, then if x and y are independent, then the probability that both these things happens factors into the individual probabilities that they happen. Now, suppose that we only know that this statement holds for singletons, and we're going to try and prove it for arbitrary sets A and B. Now, that's a big sum over all possible x sub I and y sub j of the probability that it equals those values. We're assuming that we can factor that into two things, and we can break up this two-dimensional sum into an iterated sum using Tonelli's theorem. Now, once we have the iterated sum, notice that the xi doesn't depend on the inner sum on the y sub j. So we can bring it out in front of that sum. Once we're in here, notice that when we sum over the probability that y equals yj for all yj in the set B, we just end up calculating the probability that y is in B. But now that doesn't depend on x sub I, so we can bring that out of the sum. And we're left with a sum that is just telling us the probability that x is in A. Therefore, the probability that x is in A and y is in B is the product of the probabilities that x is in A and y is in B, exactly as we desired. Now, for multiple random variables, you do independence similarly to what we did for multiple events. If I have a finite collection of random variables, x sub 1 up through x sub n, those are going to be independent if and only if for all n tuples of measurable sets a sub 1 through a sub n, the probability that all of these x sub i's are in their a sub i's is the product of the probability that the x sub i's are in the a sub i's. Extending this to a countable sequence, a sequence of random variables, x sub 1, x sub 2, etc., are independent if for all n in 2, 3, etc., x1 up through xn are independent. Now, a common situation that we run into a lot in probability is when we have a sequence of random variables that are both independent and all of the random variables have the same distribution. In that case, we're going to call the sequence of random variables independent and identically distributed, which is kind of a mouthful, so we usually abbreviate that using the initialism IID. And we're going to call it that if they are independent, and if for all I and j, x sub I has the same distribution as x sub j. The next thing that I want to talk about is what a sigma algebra of a set is. Now, remember that we called a set of logical statements a sigma algebra if the following things hold. First, if an event is in the sigma algebra, the negation of the event should also be in the sigma algebra. Moreover, if I have a sequence of events in the sigma algebra, that should indicate that the event that at least one of those events is true should also be in the sigma algebra. Now, for a random variable x, we have events of the type x is an element of A. The negation of that event, that x is not in A, is the same as saying that x is in a complement. Also, if x is in at least one of a sequence of sets, then x has to be in the union of those sets. So putting this together, this tells us that if x is in A is an event, x in a complement should be an event. And if the x in A sub I is an event, that implies that x in the union of the A sub I should also be an event. Now, this inspires the definition of a sigma algebra of sets in order to avoid having to write x in A in multiple places. So we're going to say that a non-empty collection, script F of sets, is a sigma algebra of sets if for every set in the collection, the complement of the set is also in the collection. And if we have a sequence of events in the collection, then the union, the countable union of those events should also be in the collection. And the point of this is that no matter what random variable you have, if you look at the sets that are measurable with respect to x, they should form a sigma algebra of sets. Now, any sigma algebra of sets, I should point out, contains the empty set. The reason for that is we assume that a sigma algebra is non-empty, so we pick a set in there. That means that the complement is also in there, which means if we take the complement, union the set, union the set, union the set, that inside the brackets is also a measurable set. So the complement of that is also a measurable set. But the complement of this sequence of A complement, union A, and so on is the empty set. So the result is shown. Now, unlike discrete random variables, which have positive probability of hitting particular values, continuous random variables always have zero chance of landing on a particular number. In fact, that's how they're defined. We say that a real valued random variable x is continuous if for all values A, the probability that x equals A equals 0. So how can this happen? Well, think about trying to draw a point in the interval 0 to 1. So all numbers from 0 up to 1, including 1, but not including 0. So I'm going to begin by flipping a fair coin. If it comes up tails, I'm going to move to the left half of the interval. And if it's heads, I'm going to move to the right half of the interval from 1/2 to 1. I'm going to flip the coin again and repeat, moving either to the left or to the right-hand side of the interval as the coin determines. Now, if I have an infinite, independent, identically distributed sequence of coin flips, I'm moving to the left half or the right half of the interval. And so my chance of landing on a particular number is going to be 0. That's because with each flip of the coin, the chance of landing on a particular value goes down by a factor of 1/2. And the coin is being flipped an infinite number of times. So the chance on landing on 1/3 is at most 1/2, it's at most 1/4, it's at most 1/8, it's at most any number arbitrarily close to 0. And so the chance of actually landing on 1/3 has to be 0. The result of this infinite sequence of coin flips is called a standard uniform random variable, and we'll talk more about that in the next chapter.